So we're taking every row and we're mapping it onto that subspace. So there's a, so you can actually do this projection operator. I think I'll get this right. I've got it in the notes, but this is should be A times R transpose R minus 1. So I may have the transposes swapped. But you can write this as some sort of matrix notation. But really what it's doing is projecting on the subspace. So if this green line is my subspace, then every point here is projected onto it. And then I look at that subspace, and I want to compare it to this. Okay, now A sub k, this is the best rank k subspace I can hope for based on you taking the SVD. Right, so this is rank k, and this is from SVD. Okay, and then A minus AK is everything else. Okay, so remember I drew this picture here with the singular values. Well, it's often, so this is the cumulative density function. If instead I drew this as just the height of the singular values instead, and so what's going to look like is these are going to be decaying. So as I get more and more of them, they're going to have smaller and smaller value, and maybe it gets closer down here. Okay, and so what it's saying, if I take some value k, and so k was maybe 25 or 8, one of those values where we thought we got a good representation of the face, then A minus A sub k is all of this area under here. So in a lot of situations, if you take k large enough, this is just the noise part. Okay, so I want the difference between this and the projection to be roughly the amount of noise I want it to get, plus this extra term, where epsilon is some small error parameter. Okay? So this depends on the amount of noise. The smaller amount of noise I want to have left, I want to compare it to, that's k, and I have this 1 over epsilon squared term. Okay, so this basically tells you what you can do here, and this is actually a pretty big number. You can get a slightly better air bound if you do something you can't do in a stream. You can get something that looks, instead of this bound, you can say 1 plus epsilon times A minus AK. So you can get a slightly better air bound here, where this term turned into just the tail instead of all of the mass here. But this number is really big. If I want 1% air, if I want this to be within 1% here, then 1 over epsilon is going to be 100. So then 1 over epsilon squared equals 10,000 for epsilon equals 1%. So this means you really need a lot of these rows to get a good estimate. So, people use this technique for certain tasks in machine learning when they have lots and lots of data points, and as their data set grows, they want their sample to remain fixed. So maybe they'll keep around something like 10,000 or 100,000 data sets, but they want everything they use afterwards to have a fixed running time. So as they get more, their data set never changes in size. So that's one place where you would use this. But you really need tons and tons of data points before this becomes feasible. The other interesting thing is that the rows of R are preserved here. You're getting the exact same rows. So instead of these singular vectors, these correspond with these weird pictures that look like this. Let's see here. Right, so I get this, this is what my vector, singular vector looks like. It's this weird kind of shadowy face. And sometimes these are useful. They kind of tell you something about what are the kind of the modes of variation. But they're otherwise, after you get past the first few, they're really hard to interpret what's going on. These rows are actual pictures. These say which pictures are actually giving me, are the interesting pictures. And so there's some applications where you want to have more explanatory variables where this technique is useful. But this basically has a lot of, has some other downsides to it. So this matrix here, this is rank T instead of rank K, which is what you wanted. Right? Say, I remember I could represent a face as now this 25-dimensional point that had captured it pretty well. Now I need something like a 10,000-dimensional point. And this maybe is better than having a 1,000,000-dimensional point, or maybe it's even higher than that if I have really high-dimensional space. But it's still, it's still pretty large. Okay, but it's very easy to implement. It's a very simple approach. Okay, so I'm hoping you're kind of, not satisfied with this approach. Okay, this seems to really need a lot of rows, and I'm not clear I'm really saving that much. There's not much coming out of it. So I want to mention this because up until probably roughly a year ago, this was the state of the art for what people could do for really scaling this up and saying anything formal about if you were going to have errors, what they could do. This was the state of the art until a year ago, and then there was a recent algorithm that came out that has much better guarantees and is not too hard to do. So I'm going to explain this other one next. Okay. So, and we're going to look in contrast to this number of rows we need here, which was 1 over epsilon squared times k. We're going to get to a boundary which is much better. And it turns out it's going to be basically as good as you can. Okay. So any questions on this before I move on? Okay, but this seems like a pretty obvious thing to do. If I sampled rows, how accurate would I be? It turns out you need to sample a ton of rows to get accuracy. So it's useful to know even if this is not that useful of an algorithm. Okay, so this is another streaming algorithm, and it can be worked in other settings as well, called frequent directions. And let me try and sketch out the algorithm on the board, and then we can discuss how it works here. Okay, so we're going to start with this matrix B, which is going to be L by D. So it's going to have L rows. And so L is going to be kind of a replacement for T in some sense, okay? And so it's going to, so we're going to guarantee that one row is empty. And by empty, I mean it's all zeros. So the first thing we're going to do is we're going to get A1 through a L minus 1. So it's going to get the first L of the rows, or first L minus 1 rows. So the last row is still going to be empty, right? So B is going to look like this. It's going to have data here, and then at the bottom, this is going to be all zeros. And so it's going to have L rows, and this is D. Okay, so now we're going to do for I equals L to N. So I'm going to iterate through all the rows. So this is, I'm adding in one face to my data set. I'm going to put, so I'm, let's see, I'm going to put AI in empty row of B. So the first thing I'm going to do is I'm going to have this empty row, so I'm going to put AI in the empty row. I'm going to do U SV transpose equals the SVD of B. Okay, so now I'm going to take the SVD of this. And my goal was to avoid taking the SVD, but B, remember, was small. Instead of having a big n value here, this is going to have L, which is going to be much smaller. Okay, now I'm going to create, I'm going to set this value delta, which is going to be sigma L squared. So this is going to be the last singular value of S, right? So remember, of all the singular values here, they're sorted, and the smallest one is the last one, and that's going to be delta. I'm going to set S prime is going to be equal to the diagonal of sigma 1 squared minus delta, sigma 2 squared minus delta, up to sigma L minus 1 squared minus delta, and the last one is going to be 0, and the square root of all these. Okay, so what I've done is I've taken all the singular values here, and I've shrunk them by this last singular value, and this makes the last one here 0. And then the last step, just enough room, is B is going to be equal to S prime times D transpose. Okay? And if I've done this right, the last row of B here should again be all zeros. Okay, so remember, if I multiplied USV transpose, I got B back. And I'm basically doing that. This U is just a rotation here, and it's actually going to kind of spread out these zeros to a different subspace. So I don't want to, and all I care about are the singular values and the singular vectors. So I don't care about this U vector. And when I've used these shrunken ones, it's going to guarantee that the last row will be all zeros. Okay, so one way of thinking about this is I've had these, so I started out with all of these, with all of these data points, and I've already stored in B. So let's say L was equal to was equal to 2 in this case, because that's the only thing I can draw. And so what I've done is there's variation along this direction and this direction after I've added in this last row. And I've now, the output, I've taken these, the length of these, which is described by the singular value squared in some sense, and I've shrunk them to be a little bit smaller. So this one is actually so small it's 0. So I shrunk this by the same amount here. So this amount here is delta. Okay? And so after I've done that, I'm now in a L-1 dimensional subspace instead of the L-dimensional subspace. So I wanted to be rank K on rank L. And we'll see L will need to be a little bit larger than K, but not too much larger. Okay? So it's very simple. Every step I take the SVD of this small matrix, and then I shrink it a little bit. And usually, if the data set is not too heavy-tailed, what happens is these drop off very quickly, and by the time I get to L, these are almost going to be 0. So I'm shrinking off a very small amount. Okay, so this is not too complicated of an algorithm either, I can process one row at a time. I just take this SVD, I shrink it by a little bit, and I'm going to get, with a much smaller L, I'm going to get results that look like this, but are actually going to be a little bit stronger as well. Okay, so I'll just write them down and we'll talk through them, and then, you know, so I'm going to get B, but actually the thing I want to return, so I want to return BK. And this is going to be if I took the SVD, this is the best rank K from the SVD of B. So I just want to return the top K rows, and now this will be the same rank as the matrix I wanted, A sub K. Right? Whereas before, this was some much larger rank. Okay, so let's write down these results. So I can also say A minus the projection onto BK of A. This is going to be less than 1 plus epsilon times A minus A. Okay, so I'm still going to get, and so I'm going to set L equals, so for this bound, I set L equals to K over epsilon plus K. So that one was actually some asymptotic thing, and there's some big constants. This one does not have any constants. Okay, so if I set L to be this big, by a factor of 1 over epsilon larger, I get this bound. And if I set L equals to 1 over epsilon, I can say that for any, so for any value x, I can say 0. So I can say if I want to multiply this vector, this matrix B that I've computed by any vector x, I'm close to if I'd done it by matrix A. But this one is much smaller. It's a much smaller representation. And the errors depends on this epsilon times the total for B is from A. So I'm going to kind of try and roughly explain to you why this works. So if you remember the frequent items problem where we're keeping track of these IP addresses in a string. And every time we kept these counters for the IP addresses we'd seen the most frequently. And every time we ran out of counters, we subtracted 1 from each of the counters. And we got some error in the count that was like epsilon times n. Well, that's roughly the same way how you get this bound. Okay, so what's happening is every time I get some counter, which is now going to be one of these orthogonal directions in the SVD that I don't have space for because I need to keep this row all 0, I subtract something from each of these rows. And so because in every direction, if I subtract something, I need to spread that out over all of the directions. So that's where I get the total for B is from error. So if I get some error here, it's spread out L times on the total for B is from. So this, because L is 1 over epsilon, this is this over L. Okay, so these error bounds, what exactly they mean are not too important unless you really want to verify how much accuracy you have in your algorithm. But if you want to compress and get a good estimation of the SVD with on a much larger scale, you could run this algorithm instead, where you keep updating your SVD and subtracting it a little bit. And this ensures that you don't get any kind of any error from drifting of the data.
So any hints on how you pick L?
Pick L. So you want to pick L based on, so first of all, this bound will hold for any value L, so you can actually write this instead of epsilon times this as 1 over L. So the more L you pick, the more accuracy you get, and that trades off. And you can actually write this in terms of L and K. So you don't need to know K or epsilon ahead of time. So what I would try and do is maybe get an estimation of the, so you kind of want to estimate how much you're losing when you, how much mass you're losing when you do this, and pick L large enough so you're not losing too much. So maybe start with the small L and see what kind of results you get. Maybe it's going to depend on your data set. You know, from these eigenfaces, they got pretty decent results starting with around 25 for K. So say you wanted 10% error on top of that, so maybe you pick 250. That's probably, from empirical results I've seen, that's probably more than you need. Probably 50 is going to be pretty good for most data sets. But you know, it may vary with your data set. But you can try and see. You can keep track of, one thing you know is that the Frobenius norm of B will be smaller than the Frobenius norm of A. And the difference in those is how much data you've lost. And you can calculate the total Frobenius norm of A in a single sweep over the data. So if you calculate it with the certain value of L, and you see that it's, say it's 1/2 the size of what it was for A, then you've probably lost way too much. You know, if it's pretty close, it's like 95%, then you're probably in a good range. Okay, so there's a little trick you can do to speed this up with twice as much space. I'll mention you can instead of shrinking it to size, get rid of one row. You can shrink it to half the size, and you can get roughly the same runtime with twice as much space and twice as much error. So you're going to get a much smaller runtime with twice as much space and twice as much error, but either twice as much space or twice as much error. And so there's a link to a paper which describes, you know, how do you do that. But instead of choosing the singular value L to do here, you pick the singular value L over 2, and then the second half of these are all set to 0. So then you can refill up these rows before you have to take SVD. So you only take SVD every L over 2 steps. And this will speed up the actual computation time of it. Okay, so this is basically all I had planned to cover today. I can go into the next lecture, which will be kind of related to this a little bit, the first part of that. But if people have questions on this or want to know more about it, I'm happy to entertain some topics. So this makes sense how this works? Are people, so, you know, this is one of the kind of the more advanced topics, so I went a little bit quicker, but so show of hands. Someone, if you needed to implement this in the next hour in Matlab, do you think you could do it? Let's see a show of hands. Good. Yes? No. What? I think it'd be slow in Matlab. So what language do you think it'd be faster?
I'm not sure. I know that it would be slow in Matlab.
Yeah, so one problem with Matlab is that if you're not careful, it'll try and, when you try and load AN, it's going to try and load it all at once. And so it's going to try and fit A in memory, even if you're not, even if you only want to look at it just one row at a time, right? So there are a couple of, so there are different languages, and so it depends on how you store A. If you can store A in different blocks, you can read each block one at a time, and then get rid of the other one. In certain languages, you can actually read A line by line instead of actually, or a bunch at a time instead of loading it all in memory first. So a lot of the slowness for Matlab will be in loading everything in memory. One thing about Matlab though is if you're calling the SVD operation, it's going to be just as fast in Matlab than it is anywhere else. So Matlab uses the same backend to do the SVD as other places. And in fact, there are certain optimization that does this. There are different algorithms to calculate the SVD. And you want to do different ones depending on the situation. And Matlab will kind of automatically look at your data and kind of often make a good guess of which way to actually do it. It'll say, if you have more rows than columns, it's going to know to do it with the runtime that's n times d squared instead of d squared times n. Right? So those two different ways will give you the same output. So Matlab is not going to be slower in SVD, but it'll be maybe slower in initially reading in your matrix A. And if things are too slow, what you can do is again, the simplest thing is to break it up into chunks and then read them in one chunk at a time. There may be a way to kind of read it in line, like row by row in Matlab, but I don't know how to do that. Okay, so if you have a problem doing this in Matlab, is it because you're unfamiliar with Matlab?
Yeah.
Is that the right reason? Okay, so how many people have used Matlab before? And how many people have not used Matlab? Okay, so the homework assignment on regression is going to be in Matlab, but I will kind of give you some ways on how to do it. You can do it in R or something if you want to, but you should. Matlab is pretty easy to use. The thing Matlab is not good at is in doing stuff with the for loop, because it won't. So the strange thing about one thing about Matlab is the code is not compiled, and with compiled code you kind of figure out for loops and kind of pretend and not actually have to check if I've reached the end every time through, and you can optimize certain things about it. So there's some things about Matlab that'll be slow, but it shouldn't be too much different than if you did it in C or Python, except for the input-output of reading file. And I think if you break it up into chunks, it should save most of that time. Okay, so here's what I'll do. Maybe I'll talk a little bit about random projections briefly, and then maybe on Wednesday, if I have time, I'll prep a little bit more about how to do stuff in Matlab, just so you get a glimpse into doing things. Okay, so let me use this other board over here. Okay, so there's this very kind of famous. There's this very famous technique, or this very famous property in algorithms, based on what's called random projections. Okay, and so what I'll describe is what's often referred to as the Johnson-Lindenstrass lemma often just called the JL, just called the JL level. Okay, and so what this is saying is I have data in, again, some very high-dimensional space, and I want to get down to a lower dimensional space. And kind of, this is, you know, I saved it for its related thing, but I'm going to kind of be the transpose of this in this setting. I'm going to treat n now as my high dimension and d as kind of the number of data points I have. Really what I wanted to do in both these cases is get from something that had a dimension L to something that had a dimension L. I'm from n to L, or from n to t. Right? So this matrix was much shorter in this dimension than this one. So I want to kind of compress it. Okay? And so instead now I'm going to have, so this will be a little bit confusing, all the data set now, which is going to be, again, in RD, and maybe the size, and the size of the data set is n. But now my goal is to go from D to some dimension k, which is going to be D is going to be much larger than k. Okay, so before I was going from making n smaller, and you can do kind of the same trick by swapping what n and d mean. So you're going to take a transpose of this matrix. Okay? Okay, and so the basic, so again what we're going to do is we're going to think of having this data set here. Okay, and it lies in a very high dimensional space. And I want to project it down to this k-dimensional space. And so I want to think of projecting this data, so think of like this one-dimensional space here, right? And so a projection is, again, going to be this mapping of all this data down here. Fitting onto this line. Okay, so now I have this data set P, and so now I'm going to map to this data set down here, which I'll call Q. And so we'll write that we're going to create this mapping function from P to Q, and Q is going to lie in RK. So K is going to be a much smaller dimensional space, in this case a one-dimensional space. And so from every point Pi is going to map with this mapping function down to a point Qi. And I'll explain what this mapping function means. I'll write this out more precisely, but this is kind of mathematical notation here. And the property that we want is that for all Pi and Pj and P, that the difference between Pi minus Pj, this is in Euclidean distance, minus Qi minus Qj, the difference here is going to be less than some epsilon parameter times Pi minus Pj. Okay? So this holds for all points. So for all points, if this one had a distance here between these 2 points, this is between Pi and Pj. Then I look at the same distance down here, this is Qi and Qj. These are very close. They have a relative error. And this holds for every single point. Okay, so now with PCA approaches, I kind of want points, the distance to hold on average. Some points can be really far. Like outlier points I want to be really far. This I want to say every single point has a small distance. Okay? And I want this to be a much lower dimensional space. So okay. And so how I'm going to do this is going to be kind of maybe a little bit surprising, especially if you hadn't seen any of the other tricks from randomness earlier in this class. But you're just going to pick a bunch of completely random directions and project onto those, these random vectors. And if you pick enough of them, you're going to be able to get this guarantee. Okay? So what you're going to do is you're going to pick this black one is running this. So you're going to pick k now needs to be 1 over epsilon squared times log n. So I need this many random directions, and I get the space here. Okay, so how do I pick this random direction again? I'm going to describe how I get this one random direction here, and then I'm going to just repeat this k times. Okay, and what does it mean to project down, right? So this, so random projection, I'm going to need the first thing I want to do is I'm going to get Gj, which is going to be this Gaussian random variable in RD. Okay, and so on the homework, you actually constructed these Gaussian random variables in RD. Right? You can construct D one-dimensional Gaussian random variables, stick them together, and you get this. And then you're going to write Uj is going to be Gj over Gj, the size of this. So this makes this now the length of this Uj is in the same direction as Gj, but it is its length is 1. And actually, I'm going to want to multiply this by d over k. And so d is bigger than k, so I'm growing the length a little bit here anyway. And we'll see why we want to do that a little bit. So this means that the length of Uj is going to be exactly d. So now, in order to get, so what I'm going to get is a point Q